So we've been looking at the z-distribution for some time now. Remember, the z-distribution is sometimes called the standard normal distribution. The z-distribution is how z-scores are distributed. Remember, in the center you have a central z-score of 0. That's the mean. That's the mean. And the standard deviation, remember, is 1 for the z-distribution. The z-distribution is sort of a bell-shaped curve. So remember, when you're converting from sample means, so when you have a particular sample mean and a distribution of sample means, the conversion formula to go from x bar to a z-score, we have this formula, right? Z equals x bar minus mu divided by sigma, the population standard deviation, divided by the square root of n, which is your sample size. So remember, mu is the mean of the original population. This is the mean of the population. Sigma is the standard deviation of the population. N is the size of the sample that you're going to draw to estimate the population mean, size of the sample. And remember that x bar is the average of the sample, or the mean of the sample. Yeah, so this was the formula right here for converting from a particular sample mean to a z-score. It turns out that there's some other sort of distribution that's a whole lot like the standard normal distribution, and that's called the t-distribution. T-distribution. So what we want to do, we want to define what are called t-scores. T-scores. So to get a t-score, which we'll call t, we're going to take a sample mean from a distribution of sample means, subtract the population mean, divide by the sample standard deviation, which we call s, and then divide that by the square root of the sample size n. So this formula looks a whole lot, if you go back, looks a whole lot like the formula for the z-score when you're converting from a sample mean to a z-score. The big difference, though, is rather than using the population standard deviation, right, you're going to use the sample standard deviation. And the reason why why we'd use a t-score instead of a z-score is oftentimes you don't know the population standard deviation. You don't know the sigma, right? If you have a whole entire population out there, a lot of times it's difficult to collect the data from the entire population and then compute the standard deviation of the whole population. So what we often do, we just take a sample and we compute the sample standard deviation, which is always doable if you have a sample. So this particular t-value, it's the sample mean, let's write that down, minus the population mean over the sample standard deviation divided by the square root of the sample size. So I'm writing here x bar is the sample average, or the average of the sample. N is the size of the sample size. How big of a sample we draw from, in other words. S is going to be the standard deviation of the sample. Standard deviation of the sample. So sample standard deviation, you might call it. And mu is going to be the population mean, the mean of the population. So it turns out that there's not just one t-distribution, there are many. There are many t-distributions. So imagine that this here in red is going to be your z-distribution. This is my z-distribution here. And let's say we take a t-distribution where the t-distributions are reliant on the sample size. So let's say I have a sample size of 2. My t-distribution may look something like this. So it looks a lot like the standard normal, but the tails are much fatter and it doesn't peak quite as high as the standard normal. Okay, let's say my sample size is something like, I don't know, 6. What's going to happen is the tails are going to get not as fat and it's going to spike a little bit higher. So the tails are skinnier and it spikes higher. And that's when the sample size gets bigger. Okay, let's say we take like a really big, let's take a big sample size. So we take like n equals 20. I get my purple dude here. Equals 20. Good, I got a purple. So here, the tail is going to get really close to standard normal red tail. And it's going to spike up even higher, closer to the standard normal spike. So as you can see, the bigger and bigger that the sample size gets, the closer and closer the t-distribution will get to the z-distribution. So there's not just one t-distribution, there are many t-distributions. They're similar to the z, but they're a little bit different, just a little bit different. So what we want to do, we want to look at how do you find what are called critical z-values. Critical z-values, so that's our next big task. Critical t-values. So for example, let's say I have a t-distribution here. Looks a lot like the z. Zero's in the center. And let's say I want to focus on the 95% confidence level. Moreover, let's say I have a sample size drawn, and this sample size is, I don't know, 10. We take a small sample of size 10. And let's also say that our sigma is unknown. So you only use the t when the population standard deviation is unknown. So let's say you don't know the population standard deviation. In that case, we'll use s instead of sigma. So you know it's a dead giveaway to use t's when you don't have the population standard deviation. So how do you find critical t-values? Well, the first thing you want to do, you want to find what's called the area in two tails. Area in two tails. So the area in two tails is what we want to find. So the 95% confidence interval focuses on the central 95% of t-scores. So here in the center, we have 95% of z-scores. We're going to call that 0.95. So think about how much you have in your two tails. How much do you have in your two tails? Well, out here is what we have in the two tails. We call that alpha. Alpha is what's in the two tails. Alpha. So if I take the entire distribution, which is 100%, and I subtract the central 95%, 0.95, I'll get how much is in two tails. How much is in two tails? Well, 1 minus 0.95 is 0.05, right? 5%. So if 95% is in the middle, that means in the two tails here, we have an alpha of 0.05. So that's the first thing we do. We look at the area in two tails. After that, you want to look up something called degrees of freedom. Degrees of freedom, I'm going to write that here, degrees of freedom. It turns out that degrees of freedom, I'm going to call df. The formula for that is just n minus 1. So the sample size minus 1. So I'm going to take my sample size, which was, if you look back earlier, we had a sample size of 10 here. You just take 10 minus 1. So that means your degrees of freedom here are 9. So our degrees of freedom are 9, and our area in two tails are 0.05. So that's going to give us a critical number. Let's see, our critical number is going to be called T alpha over 2. T alpha over 2. So what I like to do, I like to go into my T table real quick. So in my two tails, look at area in two tails is 0.05. And degrees of freedom, I have 9 of those. So when you look at area in two tails as 0.05 and degrees of freedom is 9, you're going to get a critical value of 2.262. 2.262. So that's my T alpha over 2. 2.262. So what that actually is, it's this number right here. It's the T value. So it's the T value that separates those central percent of 95% T values from the two tails there. It's that upper T score actually that separates. Yeah. So this would be T alpha over 2 right here. T alpha over 2. Okay.